Dear physics aspirants, right now I have the topic of alternating current and physics book. Here you will see a series of LCR circuit connected to an AC source. You will see AC voltage applied to a series LCR circuit. Figure 7.12 shows a series LCR circuit connected to an AC source E. As usual, we take the voltage of the source to be V is equal to Vm sine omega t, and if Q is the charge on capacitor and I is the current of at time t, we have from Kirchhoff's loop rule. Here is the L di by dt plus IR plus Q by C is equal to V. We want to determine the instantaneous current I and its phase relationship to the applied alternating current V. We shall solve the problem by two methods. First, we use the technique of phasors. The first technique will be phasors, and in the second method we solve equation 7.20 analytically to obtain the time dependence of I. Here you will see phasor diagram solution. Here is the phasor diagram. As you know, the relation between the phasors VL, VR, C. So LCR, you know, and I, the relation between the phasors VL and VR and VL plus VC for the circuit in figure 7.11. You will see here from the circuit shown in figure 7.12. 7.12 is here. You will see here LCR circuit. We see that the resistor, inductor and capacitor are in series. These are in series. Therefore, the AC circuit in each element is the same at any time, because they are in series, having the same amplitude and phase. Let it be I is equal to Im sine angular momentum t plus symbol is here, at where this symbol is phase the difference between the voltage across the source and the current in the circuit. On the basis of what we have learned in the previous sections, we shall construct a phasor diagram for the present case. Let I be the phasor representing the current in circuit as given by equation 7.21. Further, let VL LRC and V represent the voltage across the, what is the LRC? You know that the inductor, resistor and capacitor. Here is the LCR, LRC, and resistor, and inductor, resistor, capacitor across sources respectively. From previous section we know that VR is the parallel to I and VC is the pi by 2 behind I, and VL is the pi by 2 ahead of the I. VLRC and I are shown in figure 7.13. A, the appropriate phase relations. 7.13a, you will see here. With the help of this diagram you can understand what I am saying. Here you will see the equation 7.22, 7.223 and 7.24. The relation is represented in figure 7.13b. Since VC and VL are always along the same line and in opposite direction, they are be combined into a single phasor VCI, which has the magnitude, as the equation is here, VCM minus VLM. Since V is represented as the hypotenuse of the right triangle, whose sides are VR and VC plus I, and the Pythagorean theorem gives us this formula given by the Pythagorean. theorem, Pythagoras theorem. When you study in mathematics, then you will find this. And next is the substituting the value of the VRM and VCM and VLM and equation 722 into the above equations we have, we will find. And by analogy of the resistance in a circuit, the inductance and impedance Z in a AC circuit, you will see here, and formula is here 725B 72.26.